Okay. So let me erase this. Yuck. So just two quick announcements. There is a sheet of paper that you have to fill in about your lunch option on Friday. So everyone has to give an option. If you have lunch here, you do not. If you want to have a lunch box or so on. We need to give that back to the restaurant by noon, so please do fill the sheet. And the second thing is that there are lists as well on the blackboard at the entrance about your possibility to book taxis, to go either to Geneva Airport or to train station. So please also try to fill that as quickly as possible so that they can book the taxi. Okay? All right. So this is the last lecture about many-body physics with Et pourtant, je l'ai allumé le machin. Oui, d'accord. All right, so the platform we're going to use, once again, there are many, so don't think that what I'm saying is specific to this platform. What I'm going to say is generic to many platforms. So we've got this array of atoms, and we combine that with the resonant, with the fact that we excite the atoms to the rebirth state in order
calculations, I mean, when you involved in the Helmholtz, to get the correct answer, you still need all the phases. To keep track of all the phases. It's not like the class-wise model where you just have to have the -1.
So maybe, so thanks for pointing out. So I will show you why this kind of thing oscillates. Let's do the math. So I have an Hamiltonian, which is the sum of two terms. There is, let's say, the classical Hamiltonian, which contains just the interactions between the atoms. Okay, the sigma z, plus the delta sigma z, but let's forget about this term. And then I have this omega over 2 sum of sigma x. And those two parts are non-commuting. Okay? This I would call the H omega, let's say. Okay? What I'm really interested in is the eigenstate of this Hamiltonian, because that's the one where I do have the non-commuting part. So essentially, I'm looking at the state, the eigenstate, alpha, which have an energy E alpha alpha. So this includes those two parts. That's the result of a diagonalization that I do not necessarily know what to do if the system is complicated. All right, so now what do? At t equals 0, omega is 0. I have prepared the system in a state psi naught, which is an eigenstate of this guy. All the atoms pointing spin down, it's an eigenstate. Okay? So now, as soon as I switch on the omega, I will project onto this eigenstate. I can always write, as soon as omega is non-equal to 0, I can write that as a superposition of the eigenstate of H total. Okay? This thing now is going to pick up a phase as time evolves. So we'll have e to the minus e alpha t over h bar. And if you ask the question here, which is what's the probability, for example, to be in the ground state, or so to speak, to have all the spin back to the initial state, I measure a probability, which is psi naught psi t modulo square. And if I unwrap all the thing, what I'll have is a double sum of c star alpha c beta e to the minus alpha minus or plus alpha minus beta t over h bar. The signal I'm measuring is this guy. This is just this bit naught thing. And essentially, because all these frequencies are not rational or whatever, at the end of the day, it looks like a damping. Okay, so that's the essence of this quench experiment.
Why the damping?
Sorry, just because all these bit nodes are not commensurate. So you add many signs with different phases, and it looks like the thing dephases.
You understand why the G2 doesn't go to lower than 0.05?
Yes, this detection efficiency is the fact that because the detection was only 95%, I mean, it bumps into your face. I can show you the math. It's really problematic, and it means that despite the fact it's a pretty high detection efficiency, when you want to measure correlation function, immediately it introduces a non-negligible error. Actually, it's twice the detection error of a single atom divided by the fraction that you can put in the system, which is only 0.25. So, I mean, you multiply by 8 the effect of a single particle error on the correlation signal. So it's telling you actually the challenge to be able to measure accurately correlation function in these many-body systems. So we need to work hard on the detection. Okay? Let me illustrate now all a different aspect. So let's move towards trying to prepare the ground state of the system. So it's not a quench now. I do not want to know all the eigenenergies and all the eigenstate of the system. I just want to look at the ground state of the system. Okay? Let's look at 2D Ising model. So in a regime where essentially atoms only interact if they are next to each other. So it's what is called nearest neighbor interaction. It's not really completely true, and there's a 1 over R6. But for the second nearest neighbor, it's already significantly decreased. So you can, to a good approximation, say this is nearest neighbor approximation. And then if you ask yourself, what is the ground state when you try to fill filling the system? Well, I mean, the lowest energy that you can do is this kind of checkerboard type of array. This is what minimizes the array when you place 1/2 of the Rydberg excitation. As soon as you and this is at 0 cost, and this has the same energy as this one. And because it doesn't cost energy to put 2 atoms separated by 2 sides. If I try to add an extra one, then I have a cost to pay, which is the van der Waals interaction between a pair of nearby atoms. Of course, I have also another degeneracy. I can have the conjugate checkerboard. And actually, it turns out that, and it's much more complicated to derive, actually, in 2D. It's not even analytically calculated. It's only Monte Carlo simulation to get the phase diagram. you have a phase diagram which is pretty generic for this kind of Hamiltonian. You plot as a function of the longitudinal magnetic field, which here is the detuning of the laser. And here you plot the transverse magnetic field, which is the Rabi frequency. You plot the phase diagram. So the phase diagram means what is the phase of the system in its lowest energy state. This is the meaning of a phase diagram. So you do not care about all the other excited states to a certain extent, which I'm going to explain in a minute. Okay, so then the system always looks like this. I mean, for this kind of system, especially on a square array, you have a dome here, which is called a quantum phase transition. So there is no temperature in this problem. It's just all quantum. The ground state exhibits a transition between what is called a paramagnetic phase and an antiferromagnetic phase. So when you cross this line here, the magnetization, especially if you are here, the magnetization suddenly changes from all the atoms in the ground state to this checkerboard type of pattern. So up, down, up, down, up, down, which is called the Néel state. It's an antiferromagnet, if you wish. Okay? Right, so now this is on this line. So here all the atoms are pointing down, and when you are here, suddenly you've got this alternate pattern of the Néel state. So you've got a jump of the magnetization when you are here. If you have omega which is not 0, this becomes a continuous phase transition with a line which defines two regions with what is called a quantum phase transition once again. Okay? We could go into a lot of details about why it looks like that, but essentially you have to take it for granted because it's a bit too long to derive all these things. So this is the phase diagram of this Hamiltonian. Okay? And we want to prepare, let's say, this phase. Okay? So let's try to understand a bit more what it looks like. So I'm going to take something which is reasonably simple. Let's take a square of just 4 atoms. Okay? And I will first look at what happens if I move along this line. So I set omega to 0. And let's look at all the energies in the problem. So the Hamiltonian I have is this Hamiltonian. So at the moment, omega is 0, so I do not need to consider this term. I only consider 2 classical terms along this line. Because if omega is 0, it's a classicalizing model. Okay? As soon as I add an excitation in the system, so 1 Rydberg atom, essentially I add a term which varies as a function of frequency in energy with a slope which is minus delta. So if I have 1 excitation, I have minus delta, 2 excitation, minus 2 delta, and so on. So let's start first with all the atoms in the ground state. What is the energy? The energy, I just have 0 excitation in the system. Both terms are 0. So I just have this line here. So this corresponds to essentially all the atoms in the ground state. Let me put 1 excitation. I can put it in 4 different corners. But if I do that, then in energy, I lower the energy as a function of delta. So now I have this slope minus delta here. Okay? It corresponds to 1 excitation. It's 4 times degenerate because I could put it at 4 corners. Let's put 2 excitation. But now I have to be a bit careful. The 2 excitation, I can put them either close to each other or far from each other. Let's put them far from each other. Far from each other because I say it's nearest neighbor interaction. It doesn't cost any energy to put that. Therefore, I just have this term here. This is 0, Ni and I plus j is 0, because it only acts between nearest neighbors. So I have twice this number. So I have just 2 times the slope. But now if I look at the configuration where I put the 2 of them close by, then there is an energy cost associated to that, which is just V. Okay, so this slope minus 2 is the same here as this one, but shifted by omega. So this would correspond to an excited state of corresponding to placing 2 atoms, 2 Rydberg atoms close by. So you kind of see, and now I do the same thing with placing 3 excitation, which necessarily costs energy if I have 3 excitation. I have an energy cost which is 2 times V. So this corresponds to the second curve with a slope minus 3, blah, blah, and so on and so forth. And here you recover the dome. This is the antiferromagnet. This is here for the lowest energy, just this part. And now there is the other part where you excite all the atoms. So this is essentially a cut along the omega equals 0 line of this phase diagram. Okay? Now let's turn on the coupling. I put the non-quantum, the quantum thing. I'm going to couple those curves because this is essentially the coupling as 1 excitation in the system. You can diagonalize this system and essentially, so sorry about that, it was a problem with my computer when I did it, but what you do, because you couple those curves, you leave the degeneracy. So now you introduce gaps in the system. Okay, so essentially if I cross now here, I will show that there is a gap in energy that occurs each time I cross the second, this quantum transition phase. Okay? So now, it gives you the recipe to actually prepare the ground state. Let's do what is called an adiabatic sweep. So the adiabatic sweep essentially means that I'm going to vary slowly the parameters of the curve in a way that I do not introduce any excitation in the higher state when I sweep the parameters. And in this way, I can map this ground state of the non-interacting system to, for example, the ground state of this interacting system here. Okay? And which is to say, to prepare the nail state. So this is so this is clear, do you think? So it's an adiabatic preparation of the ground state, which can only work if you are slow. And how slow do you need to be? Can anyone tell me what is the kind of adiabaticity criteria you can guess? Yep. Yes, then, yeah. So you have a natural time scale, tau, which is kind of the inverse of the energy of the gap here. Actually, if you do the thing totally properly, and it's actually not so easy to do this calculation, but the adiabaticity criteria, you can find them in some kind of old textbook like Schiff in quantum mechanics. They do that very well. If you have two states, n and k, what you need in order, and you've got an Hamiltonian for which you vary a parameter, lambda h1, that's lambda varies from 0 to 1. So essentially here that would be just the variation of the detuning. Then the parameter, the criteria is the following one. Much smaller than omega n squared. You already know this criteria without knowing it. Just take an harmonic oscillator, the particle is oscillating, and you vary the spring constant of the spring, of the oscillator. What is the adiabatic criteria, which is to say that the thing always oscillates following adiabatically the potential? You just say that the variation of the oscillation frequency during one period with respect to the period is much smaller than 1. But this is nothing but the rate at which you vary the frequency times the period divided by omega. But the period t is 2 pi over omega. So you see that with this classical argument, you recover the quantum mechanical argument, which is it's some kind of rate of change of the parameter divided by the square of the frequency of the problem. And here it's the Bohr frequency between the two states you're looking at. Okay, so it gives this omega dot over omega squared, much larger than 1. So this is classical, and this is the quantum thing. But the two are kind of related. So if you forget completely this formula, think classical, and then you should be able to recover this one. The exact derivation, once again, is a bit more involved, and you need to look in the textbook. So let's try to do this here. So we're going to vary the parameters to cross this kind of phase transition, so we can do it at different values. So we first increase omega, sweep the detuning at a constant omega, and then decrease omega to reach the nail phase on this point. So we do that. Let's start with an array of 10 by 10 atoms. So it's a 100 atoms array. So you see it's a pretty large array already, so way beyond what anyone can calculate ab initio. And you do this experiment, you run the parameters, and you check what's the configuration you've reached at the end. And this is what you get. So here you've got missing atoms. What are the missing atoms in our language? Based on what I told you yesterday, there are atoms that have been excited to Rydberg state. So this is the staggered configuration. Okay, so this is the antiferromagnetic nail state. Of course, I lied a bit. Out of many images, I just show you the one that works. Okay? If we do it, so it's perfect, correctly, it's essentially one shot every 1,000 times that it appears. But still, you should marvel at the thing. Let's go for an 8 by 8 square array, so even a bit smaller. And you just measure at the end what are the different configurations you can get. Do you have states that are prominently dominating the spectrum? So this is all the states I can have. And you see there are essentially two states that appears with a probability of about 1%. Why is it so marvelous? Because the number of states you've got in the system is 2 to the power 64. And out of 2 to the power 64, in 2% of the time, which is a huge amount if you compare with the probability that it should be if it were entirely random, you do find the two null states that come out. Okay? Yes.
Out of the distribution.
Oui, certainly, oui, sure. Yeah. Those ones I don't know. I mean, I need to think about what they are exactly. But I mean, I think, yeah. Sorry? Oh, I'm sure there is. You also have to be careful. That's what we're trying to look at. This is why it's called work in progress. It's the detection efficiency introduced some error in this thing. So that's also something we need to care about. And it's not completely clear how to put that in the theorem. Okay. Then you can measure various observables, but I don't want to say too much about that. So I just have about 5 minutes left. So the only thing I want to tell you now are two things. First, I want to show you that, once again, all that looks like old physics. The Ising model is essentially not solved for most interesting configuration. Okay, so that's the thing you should keep in mind. So despite the fact that these spin models are very well known, there are lots of open questions. So we're not looking at things that are already completely known and that these quantum symmetry are useless. I mean, they are not, because we are now in a regime where you can really probe really open questions in these systems. I will give you a few examples. So the first thing is the classical Ising model had been solved in 1924, so 100 years ago. In 1D. In 2D, it was a major tour de force. It was achieved by Onsager in 1944. And it was completely analytical. The quantum. The quantum is was analytically solved in 1D, but only in 61. So you see, already it took 40 years to be able to solve it. So it's not that it's too easy. In 2D, it's not solved, even on a square, analytically. It's only solved numerically by quantum Monte Carlo that are pretty accurate. So we do not doubt the fact that the predictions are good, but still it's not analytical. And still, so they've been able to measure what is called the critical exponent. I mean, this quantum phase transition corresponds to, I mean, can be classified by critical exponent, doesn't really matter too much, but they've never been measured. Okay, so the only thing we know about this is theoretical. It has never been measured in 2D. The critical exponent, the position of the tip of the dome is only known by quantum Monte Carlo. It has not been measured. And now there are many geometries where we don't even know what the phase diagram looks like. We only have sketchy things, some kind of quantum Monte Carlo, which becomes harder to do, and which were only done, for example, for a triangle geometry in the early 2000s, and it has never been measured. We don't even know whether the phase transition is second order or first order when you go along the dome. In some cases, if you have what is called geometrical frustration, we are supposed to have some kind of new phases that are called liquid, spin liquids, and that have never been seen. So you see, there are really open questions immediately as soon as you change the geometry of the array. What is this quantum geometrical frustration thing? Well, think about an antiferromagnet. Antiferromagnet means that you favor this configuration. So here, if I have those two spins, what minimizes this link is just this opposite configuration. But how do you put the last one? If you want to minimize the total energy of the system, you cannot minimize pairwise. And actually, this is the essence of what is the geometrical frustration. This is the fact that you will end up with some kind of macroscopic generacy and entanglement in the system. And in certain conditions, it leads to spin liquids, which have never been measured. Okay? So now when it comes to equilibrium, essentially we know nothing. Even in 1D, when it starts, for example, the coupling start to be disordered, people are starting to study many-body localization, all these words that you've probably heard. How does the entanglement grow? There are some scaling laws in 1D. There are even none in 2D. So you see, I mean, there's really some kind of basic question that you can ask about the system that actually you cannot answer theoretically because it's very hard or very demanding, at least with the number of particles we manipulate. And now those systems are studying this regime. Okay? All right, so I'm just going to be extremely brief to give you a flavor of the second type of, so I'm not going to dive into the topology, it would be too long. I just want to show you what interesting you can do with the resonant dipole interaction and show you that you can study spin transport An idea you're already familiar with because Derek introduced that, right? But now what we're going to do is to consider only two Rydberg states. Okay, so I just completely ignore the underlying states. And we know from the point of view of the interaction that now I have this resonant dipole-dipole interaction. If I place one atom in a p state, it's coupled by a dipole transition to an s state, and you can have this flip-flop type of interactions. But this flip-flop type of interaction, I can look at it through a different eye. I can say, well, I mean, now I'm going to call a particle a p excitation. And I do single particle physics. I have two interacting atoms which amounts doing single particle physics on the spin excitation. I can say this spin excitation is nothing but a particle which hops from one side to another one with an amplitude j, which is given by d squared over r cubed. So you see, I can look at transport properties of spins through the systems in these eyes. I mean, we've done an experiment, just it's a total proof of, I mean, you can calculate this with Mathematica or in Python, whatever, in a few minutes. But essentially, you just do it on an elementary chain. You prepare one atom in the p state, all the other in the s state. You let the system evolve, and you look at the dynamics. And already with three atoms, the dynamic is non-trivial. You have only two eigenenergy, typical energy scale, V and V over 8, due to the long-range coupling. And this is what gives rise already to three incommensurate eigenvalues. For example, if you had nearest neighbor interaction, you would not see that. I will show you in a minute. So if you do the exact diagonalization, you find out that you've got these weird eigenfrequencies. It's a diagonalization of a 3×3 matrix. And what you see again is the bit knots of these incommensurate eigenenergies. If you had a 1 over R6 or a short range interaction, this is what it would look like. So very clearly, the experiment is extremely different from that, and now you're probing the 1 over R cube of the dependence of the interaction. Okay, just to give you a flavor of what kind of problem you can look at, so, and I'm not going to do anything, but essentially you can simulate problems associated with the propagation of electrons through organic polymers. So this was a problem introduced in the 1979 by Su, Schrieffer, and Eger. I mean, it was an important model because those guys and those guys got the Nobel Prize. Not for that. Eger got it for this, and Schrieffer for the BCS theory. Okay. So before, actually. Anyway, so you have an alternance of strong and weak link. And you see that if now I use the mapping I showed you before, you can look at the transport of excitation through this thing just by taking a chain of atoms and looking, exciting one, so just let me show you the configuration. You just have a chain of atoms, which exactly look like an alternance of strong and weak link. You can place an excitation here and look at how it propagates in this way. So this is now with 14 atoms. So, I mean, this model is topological, blah, blah, blah. We don't have the time to discuss that. It's not important. The only important thing is to see that with this resonant dipole interaction, I can study transport properties. But in a regime which is very interesting, in a regime where the excitations interact with each other. Because these are ensembles of two-level atoms. It means that if I have already one excitation on one atom, I cannot have the hopping of another one onto this atom. It introduces some kind of Pauli blocking, if you wish. Because you cannot excite the atom that has already been excited. So it's as if you had those spin excitations with an infinite on-site interaction. So you see that you can look with interacting Rydberg atoms at single particle physics of particle hopping from side to side, but which, when they are on the same side, interact very strongly. So in this way, it allows you to study many-body physics of spin excitations. And we've done that with this model. We have actually demonstrating the very first interacting topological phase in 1D. So you see that already this platform can look at non-trivial physics in the context of topological physics, many-body. Okay, so I will just stop here. It's just right on time. So, of course, I forgot many things that we could have discussed. And with that, we stop here. And so if you have questions, please do ask them now or later.
Is this a real image?
Yes? Of course, they are real image. We've got the full alphabet. We also have kanjis and...
Why do you want that?
Now, the only thing we haven't done, it's too bad, is the Greek alphabet. So we've got kanjis, because the PhD students have a Japanese girlfriend, so we also have all the kanjis. And, and we've got that plus... Questions? Yep?
So you said that logically you can see these interactions between the excitation as a repulsive, a stronger repulsive interaction on site. Can you also do like attractive interactions?
Yes. You can, for example, do exactly the kind of thing that Jonathan has discussed yesterday, which is this the fact that, this soft core type of interaction. So the fact that they would interact at a given distance with a U difference. So it's not only on site, it can be made soft interaction. Here, essentially what we have is what is called a hardcore boson. So there is a mapping of spin, and this is well known from theoretical physics. I didn't know that 2 years ago, but I mean, someone who had studied seriously condensed matter physics would know that. There are transformations where you can replace an S plus operator by a bosonic excitation operator. Okay? The thing is that the hardcore constraint imposes that. It imposes the fact that you cannot place two excitations at the same time. So if you try to put a second excitation, it has to be to give you zero. So this is what is called an hardcore interaction. You can also map the system onto bosons through what is called the Wigner-Jordan transformation. And look at that as an ensemble of interacting fermions. That's the reason why the word Pauli blocking is not totally wrong in this context, although you have to be a bit careful when you pronounce it. And now we can have, yes, indeed, an interaction which is beyond the hardcore boson. It's possible to have soft-core boson, which is essentially what Jonathan showed you with his circuit yesterday. You have a term UN-N-1 in the Hamiltonian, which is a soft-core term.
But it would be like a soft repulsive interaction?
Yes, yes. Or it can be repulsive or attractive, depending.
You cannot have, say, like bound states and then in the ground state. So attractive interaction that will like...
It could be attractive or repulsive. You choose what you want with this. I mean, in the case of superconducting circuit, you could not really choose because it's a naturally occurring nonlinearity. It's the fact that instead of having equally spaced, they actually have to be slightly closer due to the inharmonicity of the potential. With Rydberg, you can do the very same thing, but then it's you who choose whether you want this guy to be up or down. So you can choose attractive or repulsive. No one has ever done it, and it's just a theoretical proposal. But in principle, it should be feasible. So. Yes?
So just before the topological section, the last slide you showed us is a comparison of two fluorescent images, and on the right image, there are some missing spots. There are excited Rydberg states.
Yes.
And so are you confident that when they are in Rydberg states, they still stay in the size of grid, or do you need them to stay in the size of the grid when they are Rydberg?
I mean, we calibrate the detection, yes. So we kind of show that when we have a missing atom, within 98%, it's indeed a Rydberg excitation. And with 2%, it's not. So we have errors. So there is 2% probability that indeed the missing atom is not a missing Rydberg atom, but it's a missing atom that has disappeared during the experiment. So now that's the whole problem of the thing. So I mean, yeah. In a sense, for Patrice, his circuits do not disappear between the measurement. They're still, but for us, they can disappear. I hope so, no? Yes?
So, in the context of the transport in those organic polymers,
Yes.
Is that transport because of an electric field, or is it because just you have all these orbitals?
It's just the orbitals, yeah.
Okay.
Yes, it's transport induced by the hybridization of the orbitals. Yes.
Okay, and so is it possible to introduce some sort of electric field in?
Yes, you can, for example, try to vary the interparticle distance so that the coupling increases as a function of the position, in which case you've got some kind of natural slope. This is not what we've done here. It was an alternance of a weak and strong link, but that you can do that. Yes. Well, I mean, having said that, do not believe that this platform is fully universal. There are also other things that we cannot do, and that the circuit could do more easily, or that the ions could do more easily. For example, the ion people, they also have this sigma x, sigma plus, sigma minus type of coupling, but what they do is that the coupling GIG can be infinite range, which is interesting without being necessarily fully interesting either, because then you are back to mean field theories, but it doesn't matter. It just means that with a given platform, sure, you are reasonably universal, but not fully. I mean, you need to have all the other platforms to explore different parameter range or different types of model, even if at the end you all write under the same sigma plus, sigma minus Hamiltonian. If you ask me, how do you create an infinite range interaction? I just can't. With the Rydberg, the two naturally occurring situation are 1 over R cubed and 1 over R6. Plus eventually some hardcore things. But I mean, infinite long range we cannot do. Yet. Maybe someone will have a good idea. I think we should stop here now, Quentin, because otherwise we... so if you have other questions, I'm around, of course, until the end of the week, so we can always discuss. Good.